Welcome to the Walton Pi. Today I'm going to go through this problem from Abstract Algebra, which has to do with R modules. So, let's suppose that R is commutative and let I and j be ideals of R, so R mod I and R mod j are naturally R modules. Now, we are also going to be assuming that R has 1. Okay, so for part A, prove that every element of R mod I, tensor product of R mod j over R, can be written as a simple tensor of the form 1 mod I tensor with R mod j. So we are going to show this is true for simple tensors and then show that it works for all tensors. So let's look at A plus I tensor B plus j. Well, this is equal to A times 1 plus I tensor with B plus j, and then because we are doing tensor stuff with our modules, what we can do is this is going to commute around and this is going to be equal to 1 plus I tensored with AB plus j. Alright, and so from this means that this is going to be a valid form for part A of this problem. Now, what we have to do is now we have to show this works for all tensors. So, let's look at A plus I tensor with B plus j added to something like X plus I tensor with Y plus j. Well, these are both going to be equal to 1 plus I tensor of AB plus j plus 1 plus I tensored with xy plus j. And so once we have this then means that we are able to add the two together, and this is going to be equal to a 1 plus I tensor with AB plus xy plus j. And so that means that all elements in that can be written in the form of 1 mod I plus R mod j. Okay, so that's how we are going to be doing part A. Now for part B, how would we? Well, let's get some space. Okay, so now for part B, what we're going to have to do is we're going to need to define a function. So part B says, prove that there is an R module isomorphism from R mod I tensor product with R mod j over R, which is congruent to R mod I plus j. And then what's really nice is it gives us the mapping. So we're going to define phi going from R mod I tensor product over R with R mod j to R mod I plus j by phi of R plus I tensor product with R prime plus j is equal to R prime plus the ideal I plus j. Okay, so we're going to have a few different things that we need to prove. So first, well-defined. Why is this well-defined? Because we have a bunch of choices, we have to prove that this is well-defined. Well, what we have is from part A, each can be uniquely written as 1 mod I, so in other words, 1 plus I tensor product with some value, let's call it x plus j. Oh, we used r. We'll stick with x. 1 plus I tensored with x plus j. And so that means that there exists a unique choice for how to define the function. So just convert everything to 1 plus something, 1 mod I tensored with something mod j. And so from here we can then uniquely define how phi x. So that means this is uniquely defined, so this is going to be a well-defined function. Next step, we're going to need to prove that this is a bijection. So let's start with surjective. So to show it's surjective, we're going to first note that for all x plus no, not that way. For all x plus I plus j in our mod I plus j, we can look at phi of 1 mod I tensored with x mod j is equal to x plus ij. And there we go. That's how we're going to be able to go through and do this. So that's showing this one is surjective. Now for injective. This one's a little bit trickier, but here we go. Come on, let me scroll. There we go. Okay, for injective, what we're doing is we are going to start by assuming that phi of 1 plus I tensored with r plus j is equal to phi of 1 plus I tensored with r prime plus j. Now I'm able to write them like this because every single one of these can be written uniquely in this form. So now that we have this, how are we going to go through and show this, the rest of this? Well, if we take the product, this is, first one goes to just r plus I plus j, which means that that is equal to r prime plus I plus j. And now we have to show, why does this mean that r is equal to r prime? Well, they're equal to each other mod I plus j, and so therefore they are going to be the same. So it is injective. And now the last one is going to be showing that we have a homomorphism. Okay, so for a homomorphism, what we have is, let's look at addition first. So let's look at phi of 1 plus I tensored with r plus j plus 1 plus I tensored with s plus j. Now I'm only doing this for simple tensors because if it's true for simple tensors, it'll be true for any tensor, and so we only really have to look at this over simple tensors. So this is equal to phi of 1 plus I tensored with r plus s plus j. So this is equal to 1 times r plus s, so this is equal to r plus s plus I plus j, which is equal to r plus I plus j plus s plus I plus j, which is equal to phi of 1 plus I tensored with r plus j plus phi of 1 plus I tensored with s plus j, and there we go. So this does work over addition. The only other piece is, does this work over scalar multiplication? Come on, let me scroll a little more. Okay. Last one is for the multiplication. So let's look at phi of, and again, if this is true over simple tensors, it'll be true over all tensors. So phi of a times 1 plus I tensored with r plus j. This is equal to phi of a plus I tensored with r plus j. This is equal to phi of 1 plus I tensored with AR plus J. This is equal to AR plus I plus J, which is equal to A times R plus I plus J is equal to A times phi of 1 plus I tensored with R plus J. So we have a homomorphism that is surjective, injective, and well-defined. So we put all of that together, and we can say, therefore, phi is an isomorphism. And we are done, because we have successfully found an isomorphism that goes between the two things that we needed it to, and so therefore the conclusion of part B is done. We have successfully proven that there is an R-module isomorphism connecting those two different module spaces. I hope this video was helpful, and that hopefully this video was helpful. Please let me know if it was, and please let me know what other sorts of things you'd like me to do. And if you haven't already, please consider subscribing. It helps me to keep making these videos. Have a great day, and good luck with all of your math.